Hello, welcome to this video. In this session, we will understand Gauss law of electrostatics, an important law that relates electric flux through a closed surface to the change enclosed within it. Myself, Dr. P.V. Rajshekhar, Professor and Director, IQAC, School of Sciences and Humanities, SR University, Warangal, Telangana, India. Let's look at the learning outcomes of this topic. Obtain the Gauss law of electrostatics and to apply the Gauss law to various types of charge distributions. Before we go into the Gauss law of electrostatics, let's first have a relook at the Coulomb's law. Suppose let us say there are two charges, Q1 and Q2. Let they be positive or negative charges. As you know, like charges repel, unlike charges attract. So there is a force of repulsion or force of attraction between the two charges depending upon what type of charge they are. So according to Coulomb's law, the magnitude of electrostatic force between these two charges is directly proportional to the product of the two charges and inversely proportional to the square of the distance between the two. So the very famous inverse square law, as the distance increases, the force of attraction or repulsion decreases, or the charges come too close to each other, the separation decreases and the force increases. So essentially says that it is directly proportional to the product of the magnitude of charges and inversely proportional to the square. So if you remove the proportionality, we get a constant K, which is equals to 1 by 4 pi epsilon, where epsilon is the permittivity of the medium in which these charges are placed. If it is free space, we will write it as epsilon naught 8.85 into 10 power minus 12 farad per meter. That's a constant. So if you put the value of K in this expression, then the expression leads to 1 by 4 pi epsilon naught Q1 Q2 by R square. Essentially through this we can calculate the force of attraction or repulsion. The formula which I have considered is only by considering the scalar nature. Otherwise, the force of attraction or repulsion is directional and we need to consider the vectorial representation. But the sake of understanding, I've just considered only the magnitude of the force of attraction or repulsion. So with the help of the Coulomb's law, one can determine the force of attraction or repulsion. Through this, we can also determine the electric field intensity experienced by one charge due to the presence of other charges. So we can write E is equals to F by Q. So once we determine the force, it is easy to determine the electric field intensity. We define the electric field intensity as the force experienced by a unit positive charge. It means that let us say the Q2 charge has a magnitude plus 1, means it is a unit positive charge. And this Q1 is, let us say, positive charge and with 5 coulombs. Okay, so within the influence of 5 coulomb, positive charge means electric lines of force always radiate outward. So when you keep a unit positive charge, definitely the unit positive charge will get repelled away. With what force it gets repelled is essentially the electric field intensity that can be calculated using this simple formula. Now this Coulomb's law can be applied to only point charges, and that to static charges. Charges of point dimension are termed as the point charges. That is one of the biggest limitation of Coulomb's law, that it can be used to determine the force between two point charges or the electric field intensity of point charges which are static in nature. But what about the charges like this? If you have line charge across, spread across a line, one-dimensional charge spread across a surface, arbitrary surface. Surface means two dimension. So just like this, surface charge spread across a volume, in three dimensionality spread, volume charge. Now, this Coulomb's law cannot be applied to determine the electric field intensity due to these types of charge distributions: line, surface, and volume charge. Essentially, Coulomb's law is valid only for point charges. So that's one of the biggest limitations. There are several other small things, but mathematical difficulty, everything else. But the basic main limitation of the Coulomb's law is that it is applied to only point charges. For charges like these, line, surface, and volume, uh, Coulomb's law has a limitation. Let's see now what is Gauss law of electrostatics and what it can do. What is the advantage? So when we discussed the limitation of Coulomb's law, that it is valid only for point charges, the advantage, the merit of the Gauss law of electrostatics is that it is applicable to any type of charge distribution to determine the electric field of any type of or due to any type of charge distribution. So what it states is electric flux through a closed surface enclosing a charge is 1 by epsilon naught times the charge enclosed. Epsilon naught is the permittivity of the free space, epsilon naught times the magnitude of charge enclosed. So let's see, break this statement down into two parts. Is equals to 1 by epsilon naught times the charge enclosed. 1 by epsilon naught times the charge. Charge enclosed is Q. 1 by epsilon naught times the charge means Q by epsilon naught. And what is that equal to? The flux through a closed surface. Flux through a closed surface. So this phi is equal to Q by epsilon naught. In simple terms, let's look at this. Let's say we have a charge Q, okay, and enclosing that we have an arbitrary closed surface. Now, whenever there is a charge, to a positive charge, electric lines of force are always radiated outward. Means electric lines of force are the electric flux. Okay, how much of flux is coming out through a closed surface? That's what I want to know. Phi. If you want to know how much flux, you should be knowing how much charge is enclosed. It means to say, if you have more charge, if charge is more, automatically the flux coming out, if it is a positive charge, because flux due to a positive charge radiates outward. So if charge is more, flux is more. So to know how much flux is radiating outward, you should be knowing how much of charge that closed surface is enclosing. So essentially, the Gauss law of electrostatics states the flux through a closed surface enclosing the charge is equals to 1 by epsilon naught times the magnitude of the charge. Let's look at what this is. Phi is equal to integral over the closed surface. If we put a circle to the integral, it is a closed surface, EDS. Let's now look at the proof of that statement. One should be knowing that if the electric flux d phi means elemental flux, flux coming out to a small surface. If the surface is small, ds, the flux is also small. So this one you are seeing here, that's what is the elemental surface that we have considered. If the flux, if you consider the flux coming out through that small surface, the magnitude of flux also will be small. Area is small, the magnitude of flux is also small. Area is large. If you increase the area, the flux coming out is also large. It means to say the flux is proportional to area. And also the flux is also proportional to the electric field due to this charge. When you keep a charge, definitely there will be electric field radiated due to it, because you have a charge, electric lines of force will be radiating outward if it is a positive charge. So if you have electric lines of force, definitely you have electric field. So the flux d phi is equals to eds. Now it is not the simple mathematical multiplication eds, it is E dot ds, just like work done is equals to F dot S. So if you take away the dot, you'll get cos theta. You know, F dot S or A dot B is AB cos theta. Just like that, d phi is equals to EDS cos theta. So what we are trying to do is we are trying to get what is phi equal to. So we are first seeing what is d phi, then we can integrate it, then you'll get the total flux. So we are trying to see the flux radiating through an elemental surface ds. So that is d phi is equals to eds. Also we know that E is equal to 1 by 4 pi epsilon naught q by r square. You know how we arrived at this formula. E is equals to F by Q, force through the Coulomb's law. Force Coulomb's law has Q1 Q2 by r square. Two charges will be there, out of which one is a unit positive charge divided by Q. So one of the charge gets cancelled. So what remains is E is equal to 1 by 4 pi epsilon naught Q by r square. If you work on that, F is equal to Q1 Q2 by 4 pi epsilon naught r square, one Q gets cancelled because of the denominator. So this value of E is substituted in this expression. Therefore it leads to d phi is equal to Q by 4 pi epsilon naught r square ds cos theta. Now just rearranging the terms, what I am doing is Q by 4 pi epsilon naught at one place, ds cos theta by r square. So this ds cos theta by r square has a significance. So let's see what is that ds cos theta by r square. Now if you see here the charge q at the center of this closed surface, the distance to the surface is r, and what we have done is the electric field is radiating outward, that is E, and ds is a elemental surface. I've drawn a normal to it, that is ds. So ds and E need not be always parallel to each other. Only for a spherical surface, both ds as well as E will be parallel to each other. This being an arbitrary surface, what happens is if I consider a surface like this here, uh, this might be the electric field, and this might be the ds vector normal drawn onto the elemental surface which we have considered. So only for a spherical surface, let's say if you have a sphere, symmetric distribution, your electric field will be this, and if you consider an elemental surface and a normal to it, both will be parallel to each other. Otherwise there will be an angle made. Now, so You know what is theta now, what is E, what is ds. It's the normal projected to that elemental surface. Q is the charge and r is the distance between the charge and the surface that we have considered. Now if you see the angle subtended due to this elemental surface, which is white in color, if you observe, that is d omega. Okay, that's the solid angle subtended due to the elemental surface which we have considered. Now let us say I have increased the elemental surface, therefore the cone that is projected from the charge magnitude also increases, means the d omega also increases. Now if I consider much bigger area, and what happens is the cone d omega, angle subtended at the cone, that's the solid angle, also increases. So that value d omega is equal to ds cos theta by r square, which we have isolated. So there is a rigorous mathematical procedure to find out the solid angle subtended by the surface at Q. It's essentially the cone. Cone starts widening up as you consider more and more area. What happens is if you integrate d omega, you are trying to initially the solid angle subtended small, then increases. If you consider the total surface area of the closed surface, then it becomes a total solid angle. Okay, initially what we are doing is in place of ds cos theta by r square, we have written d omega, and the rest 2 by 4 pi epsilon naught remains the same. This is from previous expression. Initially itself I told you that we are trying to develop the expression for phi, which is the flux coming out through the closed surface. So we integrate phi is equals to integral d phi and that is integral this value, integral of q by 4 pi epsilon naught d omega. You know the value of d omega, and what is d omega? D omega is the solid angle subtended by the surface at q. If the surface increases, if means ds increases, continues to increase so that it covers the entire solid, entire surface, closed surface, then it's called as a total solid angle. So what happens is this q by 4 pi epsilon naught is constant, comes outside. Integral d omega. Integral d omega is 4 pi. Means the total solid angle subtended by the entire surface, arbitrary surface, is equals to 4 pi. And again here there is mathematical proof for that integral d omega. What is the total solid angle subtended? That value is equals to 4 pi. We are taking that value directly. In such case, the 4 pi gets cancelled. What remains is the statement which we have seen initially. That is, phi is equals to q by epsilon naught. The flux coming out through the closed surface is 1 by epsilon naught times the charge enclosed. In the simplest terms, if you want to remember, want to know how much flux is coming out, you should be knowing how much of charge is enclosed. So simple it is, means both are proportional to each other. Now we want to write it in the integral form. What I'm doing is this expression, is Gauss law of electrostatics. I want to do it in the integral form. Integral means the left hand side is written in integral form, where it is written with integration. The right hand side is not. So I want to convert the right hand side also in the integral form. What I'm doing is, if this epsilon naught is taken to the other side, something like cross multiply, it goes to the other side like this. Epsilon naught into E is D. So the same thing can be written like this. If you want to write in terms of D, its electric flux density, or we also call it as a displacement vector in dielectrics. So our aim is to convert that into integral form. Means the right hand side also should be written in with the help of integration. So we all know that Q is equal to integral V rho V dV. So it comes from this. Density is mass by volume. Charge density is charge density. I write it as rho V. Charge density is charge by volume. Charge is Q by volume is V. Okay. If there is elemental volume, elemental charge, if you cross multiply, dq will be equals to rho v dv. If you want the total charge, integrate. If you integrate, this is what we get. So volume charge density is dq by dv. So if you multiply rho v dv, dq is. If you want total, integrate that. Integral dq is q and integral rho v dv is what is remaining. So this value of q I want to substitute here. So that the right hand side also is written in the form of with the help of integration. So it becomes the integral form of Gauss law. Now if you observe, that's what is written integral EDS. If you cross multiply to the other side, epsilon naught E, it becomes D. If you don't cross multiply, this is what the main equation we have. So integral rho V by epsilon naught. Actually, it is Q by epsilon naught, but Q we have written as integral rho V dV. Okay, and if you cross multiply to the other side, we can write in the form of D, integral d ds is equals to rho V dV. So either this equation in terms of E or equation 8 in terms of D both represent the integral form of Gauss law. Essentially, the Gauss law is flux phi is equal to integral EDS for sure, that is equals to Q by epsilon naught. Instead of this q, we have written integral rho v dv, and that becomes integral rho v by epsilon naught into dv. If epsilon naught is taken to the other side, it becomes d. So what we have seen now is we have proved the mathematical form of Gauss law, and then we have converted that Gauss law, mathematical form of Gauss law of electrostatics into the integral form. Essentially, integral form sees that the left hand side and the right hand side is both represented with the help of integration. Essentially used for solving complex scenarios where charge distributions are different. Now we try to bring it to the differential form where both left hand side and right hand side is represented in the form of differential equation like d by dx. So this is what the integral form we have seen just now. Now we are using this Gauss divergence theorem. Essentially, the Gauss divergence theorem gives the relationship between surface and volume integral. Let A be any vector, we can write as integral uh, over the closed surface A ds, A is any vector, is equals to over the volume del dot A dv. Del is the differential operator that is equals to I dou by dou x plus j dou by dou y plus k dou by dou z. So it is a differential operator where it can be operated on any vector if we have, because del is I into dou by dou x. So it does that differentiation plus j dou by dou y plus k dou by dou z. So we call it as a differential operator del. So we write it as a del. Now what happens is, if you see the left hand sides are same, what we can do is equate the right hand side. So what happens in our next slide, you will see that these two will be equal. Del dot E is equal to rho V by epsilon naught. Now we observe here that del dot E is equals to rho V by epsilon naught. As usual, if you take this epsilon naught to the other side, which is a constant, we can write del dot epsilon naught E is equals to rho V. Epsilon naught E is D. Therefore, we write as del dot E is equals to rho V. So, just like in case of the integral form, we have written both in terms of E as well as both D, in terms of E as well as D. So del dot E is equals to rho V by epsilon, del dot D is equals to rho V. Now you see equation 3 and 4, we call it as differential form of Gauss law of electrostatics, or we also call it as a point form of uh, Gauss law of electrostatics. So if you see here, what exactly this del dot represents. It is a dot product. Del dot or del dot E or del dot D both represent. So you know del is a differential operator, as I mentioned, I dou by dou x plus j dou by dou y plus k dou by dou z. And what is essentially E? E can be written as, electric field is a vectorial quantity. So E is a vector. We write as Ex of I. Ex is the x component, and this is a general form. X component may exist or not. It all depends upon the scenario, which type of charge distribution, where it is Ey of j, and then it becomes Ez of k. Ez of k. So when we take a del, when it is operated upon the electric field, uh, it becomes I dou by dou x dot ex I. So I dot I is 1, j dot j, k dot k. What happens is dou by dou x of ex plus dou by dou y dou of ey plus dou by dou z of ez. So what we are doing is, through this del, we are doing the partial differentiation. We are trying to see how the electric field varies with respect to x-axis, or along x-axis, along y-axis, and along z-axis. That's the meaning of the del, the partial differentiation, dou by dou x, dou by dou y, and dou by dou z. So as we have understood previously, that Coulomb's law is limited to only point charges, whereas we have this Gauss law, which can be extended to, apart from point charge, line, surface, and volume charges also. The advantage lies in, we construct a Gaussian surface, and we consider a elemental surface over that Gaussian surface. That Gaussian surface can be a spherical Gaussian surface, a cylindrical, or a cuboid type of surface, onto which we consider an elemental surface, and then we integrate. Once we integrate, we'll get the total electric field uh, due to that type of charge distribution, be it line, surface, or volume type of charge distribution. So that's the advantage of the Gauss law of electrostatics. The only thing is, one should be able to properly identify the Gaussian surface, and once Gaussian surface is identified, an elemental surface over which the ds is projected as well as E. So what is the direction, what is the angle between electric field and ds is needs to be estimated. This is what the lecture summary, what we have seen till now. We have seen the proof of Gauss law of electrostatics, how phi is equals to q by epsilon naught. Mathematically, we have seen apart from the statement, and also we have converted that mathematical form of Gauss law of electrostatics into the integral and differential form. So both this integral and differential form are very much useful in solving problems. Integral form essentially where both the left hand side and right hand side um, in integrals, and differential form where we see the partial differentiation of how the component of electric field varies along x, y and z axis respectively. So in our next video, I'll try to explain how to use this Gauss law of electrostatics for at least three different types of charge distribution. We start with point charge, and we'll check whether it leads to the same electric field intensity that we obtained by Coulomb's law, and then we extend it to the line charge as well as the surface charge. Thank you all.